Hello and welcome to lecture number 12 in the course Advanced Robotics. In the last class, I had talked about the singular value decomposition and then a manipulation ability, that is the ability to move in a particular direction in space. And then we saw that there is a relationship between the manipulation ability, that is when you talk about the determinant of J or the determinant of J transpose. Then this is a metric which gives you the distance from a singularity also. Okay, and then we saw that when you talk about singular value decomposition, we obtain the singular values in the diagonal matrix, and the singular values indicate a lot of things. For example, the maximum singular value, which is sigma 1, shows the direction in space in which you can move very easily, and sigma n, which is the smallest singular value, that gives the direction in which you cannot move very easily. And the determinant of a matrix is also the product of the singular values. Okay, so today we'll move on and see what is the application of singular value decomposition or redundancy resolution. So how do you resolve redundancy by when you have a manipulator which is a redundant manipulator? For example, if it has more degrees of freedom than that are required to do the task. Okay, say for example the human arm, we have 7 degrees of freedom. So if I want to do a task like just catching this pen here, okay, so I want to catch it, I can catch in many ways, and the infinite ways by which I can catch. Okay, now that is possible because my hand is redundant. Okay, so I have some solutions which are I have well, I can say there are some angles which are being assigned only for catching the pen, for example for placing my fingers like this, and the other degrees of freedom of the hand are used for positioning the fingers at this point. Or looking at it in another way, I have held the pen like this, I can hold it like this and still move my hand. That means I have more degrees of freedom that side by which I can change my joint angles, but this is not changing here. So some joint angles have been assigned for to keep the fingers here to catch the pen, whereas the other joint angles have been assigned to move around and do maybe other tasks. So that is what we call by kinematic resolution of redundancy, where if you have a redundant system where there are many degrees of freedom, then some degrees of freedom can be assigned to do a particular task and some degrees of freedom can be left to do some other task. Okay, now some other task can also mean optimizing energy, for example, that do a task in such a way that the total energy consumed is optimized or minimized. Or there can be another task like, for example, obstacle avoidance. Suppose the robot has to move in a straight line. For example, I move my hand in a straight line like this, but there's an obstacle here. So I want to move in a straight line, but there's an obstacle. So what do I do? Okay, so I have to avoid this obstacle. And so what I can do is I can assign some of the joint angles for avoiding the obstacle, and I can assign some of the other joint angles for moving straight. Okay, so this is what is called partitioning of tasks. Okay, now I can move in space such that the manipulation ability is maximized. Okay, that would basically mean the energy consumed is minimized. Okay, so all these are interrelated, and I have basically explained that what is the relationship between the rank of a matrix, the determinant of a matrix, the eigenvalue of a matrix. And physically in robotics, it's very, very important for us to understand what do these things mean physically when the robot is moving in space. Okay, and we need to correlate this. So today we'll move on to the next topic, which is kinematic redundancy resolution of redundant manipulators. That is, manipulators which have more degrees of freedom than what is required to do a particular task. Okay, so as I was explaining about kinematic redundancy resolution of redundant manipulators, and we said that redundant manipulators are those that have more degrees of freedom than what is required to do a task. So redundant means what? Redundant here, it basically means that it has more degrees of freedom, more DOF than required to do a task. Okay, now let's take the example. The example is for a human being. For example, this we can all understand because we always do things like we do this with our arms. So this is my hand, and we are holding an object, okay, at a particular point, and we have 3 degrees of freedom, 2 degrees of freedom here, 2 degrees of freedom here. So we have 7 degrees of freedom. So in 3-dimensional space, in 3D space, an object has 6 degrees of freedom. Okay, so basically to manipulate an object in free space, I require only 6 degrees of freedom, and I have 7, so I have, this is redundant in a way. Okay, so it basically means to do a task, I can grasp an object, and I can also position my elbows in such a way. Say for example, I can grasp an object here, I can keep my hand here, and I can change my elbow position, okay, and still keep my fingers on the object. Now this basically means that I'm using some of these degrees of freedom. So these are 7 degrees of freedom, out of which I'm taking away maybe 3 degrees of freedom to place fingers on the object, okay, and I'm using the remaining 4 degrees of freedom to move the elbow plus shoulder. Okay, so here I'm doing with 3 degrees of freedom, I'm doing a particular task, and with the remaining 4 that are there, I'm doing some other task. Okay, and this is possible because this is a redundant system. Our arm is a redundant manipulator. Now there are many advantages of redundant manipulators. First of all, they're versatile. The advantage of redundant manipulators is, so if the system is redundant, then essentially it means in terms of solutions, so we're talking in terms of solutions, you might end up with infinite solutions for a task. Okay, so in the human arm, you can catch an object in infinite ways. Why is it infinite? Because we are having a redundant manipulator, or our arms are redundant. Okay, now redundant manipulators are used in several applications, such as obstacle avoidance. Okay, then in obstacle avoidance in cluttered environments. So suppose the arm is supposed to move in between objects and pick up an object from the table, and there are many objects. So the arm has to move in between the objects and pick up an object. So if you have only one solution, there is only one way of doing it. But if you have a redundant system, you have multiple solutions. Okay, so you can choose which solution you want. Okay. Now another example is suppose, for example, we are performing a task, for example, inspection. You are going into a boiler. So this is a boiler, just for example, and this is the inlet from the boiler. Okay, and you're supposed to go inside, and this is the outlet, and you're supposed to go in from here and do inspection. So if the robot goes in from here, it can be having multiple degrees of freedom. Okay, in there could be drums inside, or other kind of so here the manipulator goes in from here. Okay, it has multiple degrees of freedom, redundant degrees of freedom. Now when it goes into the pipe here, it loses the degrees of freedom, which basically means the manipulator cannot manipulate itself in the pipe. Okay, so it means that the degrees of freedom has been lost. But these degrees of freedom are there so that the robot can now go and perform different tasks. For example, it can go this side, this side, this side, get in there, do inspection, or catch something. Okay. Now this is a redundant system, because simply to move in free space you need only 6. But once you get constrained like this, where the degrees of freedom are being lost, then you have to add them to the total system. Okay. Now these are the advantages of what we call redundant systems. They're also called snake robots, having very, very large number of degrees of freedom. So they can crawl into different places, difficult places, do difficult tasks, and things like that. Okay. So here we are dealing with a system which has more than 6 degrees of freedom, and we are trying to find out there are 2 ways of solving this problem, what we call redundancy resolution. So the word is redundancy resolution. So how do we resolve the redundancy of these manipulators? Redundancy resolution. Okay, so there are 2 ways. One is let's talk about this as one case. Okay, where okay, now before I go there, before I move into this, x dot is equal to j into theta dot. Okay, for a redundant system, j is non-square, m into n. Okay, so if you're trying to control the manipulator or move the manipulator using, in terms of the control, you have multiple solutions now, because j is non-square, and depending on where you are in the workspace, you get particular solutions. You can choose your solutions. Now let's look at 2 cases. The case 1, where we are trying to resolve redundancy, where we are given a manipulation vector that is given by y is equal to f of q. Okay, that means y is a function of q, which is similar to this. Okay, now so this is the main task. Okay, for example, let me give an example. So I have a manipulator which is a 3 degree of freedom manipulator, which is redundant, and it has to move in a straight line. For example, I have a manipulator which is like this, and it has 3 degrees of freedom, and it has to move down in a straight line like this. Okay, this is an example. I'll solve this example after some time as we go along. There's an obstacle here. So you can see that when the manipulator is coming down, the end effector is coming down. This manipulator is going to come down. This will come down like this, like this, like this. Then if it comes down more, it is going to hit that obstacle there now. Okay, so it has 3 degrees of freedom. So what we can do is we can divide this task into 2 parts. The first task is to follow the straight line. Okay, so this is my main task. So main task and subtask. So main task is follow straight line, okay, by the end effector. So this is my main task, which is given as 1. Now what is the subtask? Is avoid obstacle. What is the subtask? When it is coming down following the main task, the manipulator should be such that it should not hit the obstacle there. So you can imagine what it can do is after a particular length, it has to start moving in the other direction. Okay. So by changing its orientation, what it is doing is it is following the straight line, but it is also avoiding the obstacle. So this is my task 1, follow the straight line. Task 2 is avoid that obstacle. Okay. So this is not possible in the case, this may not be possible in the case if the system is not redundant. Okay. So here it is a redundant system. So we have some degrees of freedom which can be assigned to follow the straight line, and the other degree of freedom can be assigned to avoid the obstacle, and together they are performing the task. Okay, so this is one way by which we can say that we are dividing the total task into two tasks. One is a main task, one is a subtask, and the problem is being solved. Now here, coming back here, if I take theta dot is equal to j hash into x dot plus j hash into j minus I into lambda, this is the solution for theta dot. Now this can become my main task. Okay, and this is my subtask, or let's call this the subtask or secondary task. Okay, so this means that the solutions that I'm getting from here, they constitute the main task now. Okay, this is and this constitutes the secondary task now. So I'm going to divide my degrees of freedom into 2 parts, assign them accordingly, and the task is being performed. Okay, this is one what we call the case 1. In case 2, this is my case 2. Now in case 2, we may be required to do some kind of an optimization. For example, there could be a criterion function. Okay, maximize or minimize criterion function. What does this mean? This means that when it is moving in space, for example, or doing a particular task, you maximize or minimize something like an energy, Okay, so maximize or minimize the energy. So maximize and minimize what? It can be maximize or minimize energy. Okay, it could be maximize or minimize manipulation ability. So we know what is manipulation ability, which is equal to V of Q or W. We define manipulation ability as W of Q to be equal to determinant of J transpose. Okay, so I can maximize or minimize this. How do I do that? Suppose I want to move in a particular direction, okay, such that this is my 2-link manipulator. Now let me take this example. This is a 2-link manipulator, like your finger, like our arm, or like our finger. Let's talk about our arm. So this is my arm, okay, and I want to move in such a way that this is getting maximized. So what I do, I can take the derivative of this, and each step, wherever I am, the next step, I'm going to find out which direction this gets maximized or minimized. Okay, so I'll come to this example as we go along. So we have a criterion function, and I can take the derivative of the function, the dw by dq. Okay, this is the gradient, and follow the gradient. Okay, so this would mean that the manipulation ability will get maximized. Okay, so one way is by dividing it into tasks. The other way could be by increasing the by optimizing a function, and that function can be manipulation ability, it can be energy, it can also be distance from singularity. Okay, so keep away from singularity. Now in the case of this manipulator, for example, this two link manipulator I've drawn, suppose I'm at this instant at time t1. I want to move in a particular direction in which it is easy to move. So what I can do is I can find my manipulation ability ellipsoid and see that this is the direction in which I can move easily. So this is the direction in which I cannot move. This is my sigma 1, sigma n. So I can move easily in this direction. So I move, the next point would be here. Then I find the ellipsoid again and follow it, which is equivalent to saying this, that you find the gradient of the manipulation ability ellipsoid and start following that. Okay. So when you grasp an object, when you move your arms, we are actually doing this. So we are minimizing energy. We'll see how. Okay. So let us look at the first case first. Okay, so we are looking at case 1. Okay, main task and subtask. Now this means that let us define this as y1 is equal to j into y dot is equal to j into q dot. Okay, this is equivalent to saying x dot is equal to j into theta dot. Okay, so here is my y1, j into q dot. Okay, there, this is equal to that, that is equal to that. Okay, so this is my main task. So main task 1 is to follow this trajectory which is defined by y1 dot is equal to j into q dot. Okay, where j is the Jacobian matrix. Now Jacobian we have seen is let me also write it here, j is equal to m into n. So it's a redundant system. So in this case your q dot becomes equal to j1 hash into y1 dot, let's call it first task, so let me call it first task desired, plus I minus j1 hash into j1 into k1. So what we have done is, from this equation I want to find what is q. So q is equal to the pseudo inverse of j1. Okay, let's call this j1. So pseudo inverse of j1 into sorry, this is one part which we get, and this is my null space. So that is my null space, and k1 is a constant. Okay, now in this equation there are multiple solutions which will satisfy this. Now let us say second task. So this is my first task. The second task is given by y2 is equal to j2 into q dot. This is my second task. Okay, now we can call it y2d. Okay, now here also what I can do is I can take, so y2d, what I can do is I can take the previous equation and put it into this equation. Okay, so y2d is equal to, so what I'm going to do here is my q was here, so I'm putting my q into there. Okay, so what I do get is y2d is equal to j2 into y1d. This is equal to, so I'm putting this one in here, j2 is there, and j2 will get multiplied into this also, so I get another term plus j2 into I minus j1 hash j1 into k1. Okay, so what I did is I took this q dot and I put it inside here. So there is a j2 there, which is for the second task. Now I can write this as y2d minus j2 into j1 hash into y1d is equal to j2 into I minus j1 hash j1 into k1. Okay, now suppose I want to find the value of k1. No, I want k1. Now see, if I want k1, what I can do is I can take the inverse of this again. So this is what I'm going to write it as. I'm going to write all of this full equation as j2 hash. So this full term, I'm going to write this as j2. Okay, I'll call this j2 hat, this full term. So what it is coming out to be is, let me write it here again in the next page. So it is y dash 2d minus j2 into j1 hash into is equal to j2 into I minus j1 hash into j1 into k1. So what I'm doing is I'm writing this one as j2 cap. Okay, so what will be my equation? My equation is going to be y2d minus j2 to j1 hash y1 dot into y1d is equal to j2 cap into k1. Now if I want k1, what do? I take the pseudo inverse of this again, so I bring this side. Now J is a non-square matrix, right? So when J is a non-square matrix, what is happening is that you end up generating another K1 is equal to, I'm going to take K1 J2 on the left hand side is equal to J2 hash now, which is the pseudo inverse of, so y2d minus J2 into J1 hash y1 dot d is equal to, plus, so this is the main part, plus is going to become I minus j2 cap into j2 cap hash into k2, another equation. So here, just to explain what I did, x dot is equal to j into theta dot. So theta dot is equal to j hash into x dot plus I minus j hash j into k. This is what I'm doing. So in this equation, if I want to find what is the value of k1, a constant k1, I have to bring j2 this side now on the left hand side. That means take the inverse or the pseudo inverse and multiply. Okay, so what I get, k1 is equal to this full term into j2, which is here, plus I get this term because j2 is a non-square matrix. So I get this one which is coming here now, which is equal to k2. Okay, so my q d is equal to j1 hash. So the value of what I am doing is I'm going to take the value of k1 and put it inside here now. Okay, so I'm taking the value of k1 and putting inside here. So what I get, the desired q dot is equal to j1 hash into y1d plus j2 hash into y2d minus j2 j1 hash into y1d plus this is I minus j1 hash j1 minus j2 hash j2 into k2. This is what I'm getting from here. Okay, now what is the meaning of this? Let's try to understand the physical meaning of this. One part is the maths part of it, but let's try to understand the physical meaning. The physical meaning of this is that whenever there is a matrix J m into n and you're trying to invert it, the solution is this. So the solution will always involve two parts now. So when we first wrote our solution, let's go back there. Let me explain what I did. We first had our first task, which is given this by this equation. Now J is non-square, m into n. So when I found q, which is the joint velocity, okay, so by integrating the joint velocity, you can get the position, right? So if you're at a particular instant, but incrementally, you can get the next position by incrementing it. Okay, so here what we're getting is, when I'm trying to find what is q, then because j1 is non-square, what I'm getting is one term is this and the other is that. Okay, so homogeneous solution plus particular solution, okay, in the null space. Okay, so I'm simply using this equation repeatedly. X dot is equal to j into theta dot is equal to j hash into x dot plus j hash j minus I into k, into lambda or into k in this case. Okay, so from here I get this because j is non-square. Now I want to find what is this. K1 is a constant, so I define another term. I define another task which is given by y2d. So my first task is y1d, the second task is y2d, j2 into q dot. Now I take this q dot and put it here. So what I get is this equation. Okay, and there is a k1 there. Now if I want the value of k1, what do I do is I bring this on the left hand side, and then I want k1 now, value of k1. So if I want the value of k1, this fellow is also non-square, m into n. So what I take its pseudo inverse and bring him on the left hand side. Okay, now if I do that, I'll get another two terms again, this plus that. So I'm getting one term here plus one term there. So I'm simplifying, I'm getting this now. So this is giving me, and then what is happening, I'm taking the k1 and putting it back in there. I'm taking the k1 and putting it back in. So I've got my k1, and then I'm putting this k1, I'm putting it back there, and I'm getting in terms of k2 now. Okay, so this is the one task, this is my secondary task, and this can be my tertiary task. So the first task is this one, second task can be this one, and this can be a tertiary task also. If you have more degrees of freedom, you can do more tasks. Okay, so let's so this one, what we can do is we can simplify it and write it this way. I'm simplifying it and writing that q dot d is equal to j1 hash into y1d plus I minus j1 hash into j1 into y2d. Okay, so this is my main task, and this is my subtask. This fellow is my subtask, which is this one. Okay, now we'll have a look at one example of this and see how we can use this. Now what this basically means, let me give you an example here. Suppose I have a snake robot, a robot having multiple degrees of freedom, 10 or 12 degrees of freedom or even more. Okay, so what I can say is that this is following a particular trajectory like this. Okay, the arm, and now to follow this trajectory I probably need 2 or 3 degrees of freedom only. The remaining degrees of freedom could be doing something else. For example, they could be forming like this, or it could be forming like that. Okay, so some degrees of freedom here are performing a task. Let me call this the first task. Some other degrees of freedom are doing a secondary task. For example, let me take a better example. A better example would be, suppose there is an obstacle. There's an obstacle here like this. Okay, so when the arm is coming down, you can imagine this, the arm is coming down, okay, here and here. Now the arm has to come down further. If the arm tries to come down from here, if this link and this link comes down, both of them, there's a chance it will hit this now. Okay, so what it can do is it is going to use the degrees of freedom here to position the end effector on that line, but it will use the other degrees of freedom to have a posture such that like this, like this, like this, and like this now, so that it is avoiding the obstacle now. So it was using some degrees of freedom to follow the line, and it is using other degrees of freedom to avoid this obstacle. For example, if there is a narrow passage like this, so there's an obstacle on this side, there's an obstacle on that side also. Let me put some other color here. Maybe there's an obstacle here, and there's an obstacle there now, but I want it to follow this straight line. So it has to keep away from this and keep away from that also. So it is using some degrees of freedom to do this task. It is using other degrees of freedom to do that task. Okay, so there can be many examples of this where say for example there is a passage like this, and the robot has to go here. So it is coming like this. Okay, it goes through here, goes here, goes here, goes here, goes here, and maybe it does a particular task. Now the moment it has gone here, what has happened is it has got constraint. It can't move there, it cannot move there. So what it is doing is, to catch this object, it is using these degrees of freedom, and to position itself there, it is using other degrees of freedom. So this is my first task, that's my second task. Okay, so now I hope you understand the meaning of first task and second task. Now let us look at the second example, case 2. So case 2 is subtask given by a criterion function. Subtask given by a criteria, given by a criterion function. So let's say that the criterion function is k1 is, so let me come here. So q is equal to, so q is equal to j1 into q1 dot, sorry, y1 is equal to, so q So q1 dot is equal to our equation j1 hash into y1 dot plus j1 hash into j minus I into k1. Now suppose this k1 is given by a criterion function, for example eta into kp. Okay. This is a criterion function. Okay, and eta can be consisting of 1, 2, 3 different functions, sub functions. Okay, then what I can do, eta would be equal to, I can put it this way, dvq by dq. Okay, so this function v can become equal to w, or the manipulation ability, which is equal to determinant of jj transpose. So if you're supposed trying to optimize manipulation ability when you're moving, then what we can do is we can take this here, take this one and put it there. Okay, so when you're moving, what is happening is, this is your first task, this is your second task. So your second task is optimizing manipulation ability, or following the gradient of manipulation ability, and this is solved as an instantaneous optimization problem. Okay, this is one way of by which we can optimize the manipulation ability when we are moving. So if you're in a particular location, okay, so we are in a particular location, for example we are here, okay, you find the Jacobian, okay, find the manipulation ability, determinant of jj transpose, and take the derivative, so which will become dw by dq. So this is and then follow the gradient. So what would happen is, when this manipulator is moving in a particular direction, what is happening is manipulation ability is getting maximized. Okay, so let's look at a very simple example. Okay, let's look at a very simple example to give us an idea of how this can be used. We are interested in using both these formulations. So the first one is this example, which I had just talked about some time back, that we have a manipulator like this. Okay, and there is an obstacle here. And what is the task? The task is this manipulator should move down like that. Okay, so this is my x-axis, that's my y-axis. Okay, let's say this is 1, that is 2. Okay, link length is 1 and 1. Okay, this is link length is 0.3, and this is my desired trajectory. Okay, so this is my desired trajectory, and let's say this is 1 unit here. Okay, so this is my theta 1, that's theta 2, that is theta 3. Okay, so I am going to and this is 3 degrees of freedom manipulator. So it has 3 degrees of freedom, some of which can be assigned to follow the desired trajectory by the end effector, and some of it could be assigned to avoid this obstacle. Okay, so the link lengths are given here, 1, 1 and 0.3. Now at the beginning of the task, the initial configuration at time is equal to 0. So let's say the initial configuration, okay, so q naught is equal to 20, 30 and 20 initially when it is starting. So this is 20, 30 and 20. Okay, and which corresponds to r naught, the position which is equal to x naught, y naught. You can compute this, it becomes 1.69, 1.39. You can compute. So this point is 1.69, 1.39. Okay, that's my initial position. Now we can find the Jacobian. So the Jacobian of this is equal to, initially we can write x and y equal to, x is equal to L1 cos 1 plus L2 cos 1 2 plus L3 cos 1 2 3, and y is equal to L1 sin 1 plus L2 sin 1 2 plus L3 sin 1 2 3. So when I take the derivative, I get J1 equal to minus L1 S1 minus L2 S1 2 minus L3 S1 2 3 minus L2 S1 2 minus L3 S1 2 3 and minus L3 S1 2 3. Okay, similarly I get the second term, which is equal to L1 cos 1 plus L2 cos 1 2 plus L3 cos 1 2 3. Second would be L2 cos 1 2 plus L3 cos 1, 2, 3, and the last one is going to be plus L3 cos 1, 2, 3. So this is my Jacobian matrix. Okay, now what we want is that it should follow this trajectory without hitting the obstacle. Now, so what it needs is, I need to follow the trajectory, without hitting obstacle. Okay, so I need to find this, so let me mark it in red. This is the trajectory I want to follow. This is the trajectory I want to follow. So what is the equation of the trajectory? So y1d, which is going to be my first task, y1d. So y1d in terms of time is the trajectory I want to follow. Now what is the trajectory? You look at x0 is constant. Okay, so x0 is a constant, right? It is a straight line coming like this. So x0 is constant, only y is varying. Okay, so y is varying. Now x0 is constant and y is varying. What is the trajectory? It is equal to y0. So the trajectory here is y0 minus 3 minus 2 t into t squared y0. Okay, how did we get this? So what we are doing is, just to sidetrack, we are fitting a cubic polynomial to the trajectory. So it basically means that I'm fitting a cubic polynomial. So y in terms of time t is equal to a0 plus a1t plus a2t squared plus a3t cubed. Okay, this is a cubic polynomial I'm fitting onto the y. X is a constant, x is y0 only. And I'm putting initial conditions. Initial condition would mean that it is starting from some value of y initial. Okay, so at time is equal to 0, okay, it will have some value. Let me call it, it was at some y. Okay, so let's call it y initial. At y final, at final time, what is the final time at yt? It is at y final. Now at start and at end, y0 initial is equal, velocities are equal to 0 and y0 is equal to 0 again. So start and end, there are two conditions, velocities are 0, and the two positions here are initial start point and initial end point. So if I take the derivative of this, y0 t is equal to, I can take the derivative of this, then I get the velocity. So I'll come to in details about how to fit the cubic polynomials, okay, when we talk about trajectory planning. But here just understand that what we are doing is we are fitting a cubic polynomial onto this trajectory. So there is an x and a y, right? X is a constant. Y we are fitting a cubic polynomial. Okay, and when I fit the cubic polynomial, I write this cubic polynomial this way, and there are four conditions: initial position, final position. Okay, initial position at time is equal to 0, at final position at time final. There's two conditions you get, and another two conditions are velocity at start and velocity at end are 0. So using this four, there are four constraints here. So you can find these four constraints by using these four conditions. Okay, so what we get is this equation. So this is my first task. Okay, task 1. Now if you have a task 2, okay, the task 2 is avoid obstacle. Now avoiding obstacle, what does it mean? Avoiding obstacle basically means that I give it some orientation which it cannot cross. So I give it some limit and say that this is the limit which it cannot cross. Say for example, I give it this configuration. Okay, so this is my limiting case, by saying that my second task should be such that it should be near this configuration. Okay, so second task, avoid obstacle. How do we avoid obstacle? So configuration nearest to desired configuration. Okay, so configuration nearest to desired configuration, what does it mean? So when it is moving, the configuration should be nearest to this one, okay, the closest to this. Now that would basically mean that it is keeping away from the obstacle now. Okay, so keeping configuration nearest to that would mean that I have to give the configuration variable y2d the angles basically. So 45 degrees, minus 70 degrees, and 0 degrees. So it should, so when it is moving, so let me write it, when an arm is moving, it should be closest to this configuration, which will ensure that it doesn't hit. Okay, so next, if I take the derivative of this equation, so I've written the position equation, let me take the derivative of this. I get q dot d is equal to j1 hash into 0 minus 6 1 minus t into y naught plus I3 minus I1 hash into j1 into h2 into y2d minus y2. Okay, this is a constant. What is this? This is the difference between the present position and the desired position. Let me draw it here and explain. So this is my desired line I'm supposed to take. Okay, this is my arm, that's my arm. What is the constraint I have put? That it should be nearest to this constraint. It should be nearest to that. Okay, so what it will do is it will try and find a solution. Okay, it will find a solution here, my main solution, such that this arm is following the straight line. That's my main solution here. And the second solution is the difference between this angle and this angle now. So it got a solution. Maybe it got, let me say it got this solution. Okay, it got, it was at this position. Next position is, it is getting this solution. Okay, so this part is this one now, the first part. The second part is it will minimize the angle difference here now between this and this now, and between that and that. So this is the second part, which is minimizing or trying to make the solution go close towards this red line. Okay, minimizing the difference in angle. Okay, so if you do that, then what happens, what we see is that, let me draw it and explain it here. Now in the previous case, we are taking q dot d. So if you integrate this, you'll get position. So how does this work? It starts off from here. Okay, let me explain how it works. Basically, it is working starting from here. This is the point where we are. Okay, it uses the equation. We have found the Jacobian. Okay, so what we need is q dot. What we need is q dot here. So what we need is q dot. So what we need is this. Q dot is the velocity. So if I integrate that, I get the next position. So how am I getting that? I'm actually taking the pseudo inverse of the Jacobian, finding the trajectory that I'm going to follow at the next instant. So next instant, this is my point. I was here, this is my next instant. So this is one solution that I'm getting. And then whatever solution I have got, I'm taking the difference in the angles between the constraint that I have to try to keep near to and the present solution, and trying to minimize that. Okay, so what we are getting is, if you see, if I do the inverse kinematics this way, okay, so this was my initial position, and if you're just coming down like that, it is going to come down like this. Okay, so this, the manipulator is just coming down. Okay, it has followed the straight line, but the manipulator has just come down without a constraint. So it is following the straight line, yes, but then it is just coming down, and there is no, if there is no obstacle. The moment I put an obstacle, what would happen is, so this is y1d, this is desired task. What happens if I put an obstacle? What will happen is I have an obstacle here now. So I'm supposed to follow the straight line, which remains the same, which is the first part of the problem. Now it starts coming down. So it starts off with this solution. The starting solution is the same there, but then what happens is it changes its configuration. Okay, so it changes its configuration to the other side. So basically it is coming to the other side now. Okay, or okay, so it is doing this one now. So what it has done is it has changed its configuration, and then it is coming down now. So in this case, there was only one trajectory that I'm following. Now in this second case, I am following this trajectory, but I'm also keeping away from this obstacle. And how am I doing that? I'm doing that by saying that my first task is to follow this obstacle, which is my y1d. Okay, the second task is that I have to keep near to the constraint. What was the constraint? This was the constraint, so this is my constraint. So it has to keep near to that. So whatever solution is here, it has to keep near to that. So it will start choosing solutions which are near to this solution now. Okay, and how is it doing that? It is simply doing that by looking at the angle difference. Okay, so what it is doing is trying to minimize that, and the result of which is giving you this solution now. Okay, so this is an example of redundancy resolution with using the case 1 and the case 2, where we are giving it a subtask and it is following the subtask. Okay. Now we can also follow the second. We can do the second case where we have a manipulator. Okay, let's look at this example where we have a manipulator which is avoiding singularities. Okay, now it is avoiding singularities means what? It is keeping a distance from singularities. So keep a distance from singularities, or keep the farthest distance from singularity. Now we have seen that a distance from singularity, so distance metric, which is the distance from singularity, is equal to your manipulation ability. Okay, so basically if I write my function VQ to be the manipulation ability, determinant of J into J transpose, okay, then what I can do is I can find the derivative of this dV by dQ and follow that. Okay, this will become my constant. So in my equation, x dot is equal to J into theta dot is equal to J hash into x dot plus I minus J hash J into K. So this one is this one now. Okay, so what it is going to do is it will move in such a way that it keeps away from the singularity. Okay, because if it is maximizing the manipulation ability, means it is keeping away from that. So you just follow the gradient of the manipulation ability, and that will ensure that you're keeping away from singularities. Okay, this is a very, very important topic in terms of redundancy resolution of redundant systems. Now, if you look at the arm, if you look at our human arm, we always move in such a way that the arm is optimizing the manipulation ability. Okay, now if you look at another example, this is just to convince you that all biological systems actually do this. We also do this unknowingly, that we are moving such that manipulation ability is getting maximized. That means you are keeping away from singularity and you are also consuming the least amount of energy. So when you are grasping an object using fingers, okay, so if you suppose I have an object here and you are grasping an object using your thumb, so let's say this is my thumb finger, this is my thumb, and this is my index finger. Okay, so this is my thumb and that is index. Let me draw the index finger here. So this is the index finger. Okay, so this is my index finger. Now the index finger has 3 degrees of freedom. If I see it as if I consider this to be planar. Okay, so this is thumb and this is index. I'm just grasping an object. You can imagine that you're holding an object. Okay, using 2 fingers, and this is my index finger. Okay, index finger has 3 degrees of freedom. 3 degrees of freedom on the plane. It actually has 4, but on the plane it has 3 degrees of freedom, if you understand what I'm saying. So the question comes that if I have a 3 degree of freedom system, this is my 3 degree of freedom system. Okay, 3 degrees of freedom, like that. Okay, so this is 1, this is 2, this is 3. This is my object. Then because this has 3 degrees of freedom and for a point you only need 2, x and y, this is a redundant system. So the index finger is redundant provided it just wants to apply the fingertip at a point xy. Okay, so when you hold an object, if you notice how you hold an object, you'll always note that your finger orientation is like this, the way I have drawn it. Okay, you will not hold it, you are not going to hold it like this, okay, or this one is straight down like this. We don't hold like this. Or there are other ways by which you can hold. This can become like this can become like this, and this can become like this. They are all holding the object. Okay, so it basically means that there are large solutions here, large number of solutions. Okay, why? Because it's a 3 degree of freedom system. So which solution are you going to take? Or when you grasp an object, which solution do you take? You'll always note that you take this solution, and this is the one that gives maximum manipulation ability. So this gives maximum manipulation, or rather maximum manipulability value. Okay, so whenever we hold an object, you use your fingers to hold a grasp an object, it is always seen that we maximize the manipulation ability. And when we follow a motion in space, okay, when you're moving your fingers, what you're doing is you're following the gradient of dw by d theta. Okay, this is what our k1 is this. So it has been proved that when human beings move our fingers, we move our arms, we are always moving such that your manipulation ability is being maximized, and we are following the gradient of this, because of which the manipulation ability is being maximized. Okay, so this is a little difficult topic in the sense that you need to be very clear of pseudo inverses. What do they mean? When there are multiple degrees of freedom, what do you do? Okay, so this is a little difficult, but when you understand it very clearly in terms of the pseudo inverse and the relation between the singular values, the pseudo inverses, then it becomes easy to understand. In terms of practical application, this is of very, very high importance, because very often you have redundant systems, and very often for example, our arm is also redundant. Okay, and in the case of a manipulator, even if it is 6 degrees of freedom, the task may require less degrees of freedom to do the task. So in which case you have to assign, or you have to do the task such that you consume minimum energy. That means you use the least number of joints. Okay, and you can assign the other joints for doing some of the task. In the case of obstacle avoidance in cluttered environments, for example, in robots like snake robots, where there are very large number of degrees of freedom, in such cases we can always assign, we can break the whole task into main task and subtasks, and in all such cases the Jacobian is non-square. So please remember that whenever you turn up with or you're dealing with a non-square Jacobian, this problem comes up, and this is the way we solve the problem. So we'll stop today and continue in the next lecture. Thank you.